When we talk about climate change, carbon budgets, most people think oceans, maybe forests, right?
Right, those are the big visuals.
But the real heavyweight champion of carbon storage, the biggest pool on land, it's actually the soil, right under our feet.
It is. Soil organic carbon, or SOC. It's massive. Holds more carbon than the air and all the plants combined.
Wow.
And, the critical thing for you, the listener, to grasp is just how much human land use affects this huge reservoir.
So today, we're diving into global research that shows how fragile it is. We're going past just like total carbon numbers. We're asking, how much carbon do we lose historically? What form is the carbon in now? Is it the easily lost kind or the stable stuff?
And crucially, who is managing it down there? Which microbes are calling the shots?
Exactly. Our mission here is to give you a clear, quantitative look at what happens when we mess with land or try to fix it, focusing on those carbon types in the microbes, especially that bacteria to fungi ratio.
Yeah, that BF ratio is key.
Okay, let's unpack this, starting with the big picture loss. When we first converted, say, a forest or a prairie to farmland, what was the scale of carbon loss? What's the global debt?
The debt is huge. A legacy issue, really. Globally, the estimate is around 116 gigatons of carbon loss.
Just from the top 2 meters.
Just the top 2 meters, yeah. 116 GT. It's a, staggering amount.
That's like decades of fossil fuel emissions just gone from the soil. And the specific conversion numbers are pretty stark too, right?
There really are. You see clear patterns. Turning natural systems into cropland hits carbon hard. You've got tillage, less plant stuff going in.
So forest to cropland, what kind of drop are we talking?
Typically, you're looking at losses somewhere between, say, 25% and maybe 32% of the original soil carbon.
And grasslands, similar story.
Pretty similar declines, yeah. Maybe 16% to 36% loss. It's that combination of disturbance, simpler plant life, and just, burning off that stored carbon faster.
Okay, so that's the bad news. But the sources also talk about restoration, reversing the trend. That seems more hopeful.
It definitely is. The potential is there. If you take cropland and turn it back into forest afforestation, you can see gains up to maybe 57%.
57% gain. That's huge, especially in degraded areas.
Exactly. Particularly strong potential in degraded tropical soils.
Yeah.
And going from cropland back to grassland, that's also positive, maybe around a 26% increase over time.
Okay, those numbers sound good, but here's a crucial point the sources raise. If it takes, 80 years or even longer for soil to reach a new carbon balance?
That's the time scale.
Can we really count on soil sequestration to meet, say, 2030 climate targets? Or even 2050? It seems incredibly slow.
That is the hard truth. It's slow. We're talking multiple decades, maybe generations. Soil carbon building isn't a quick fix. It's vital, yes, but it's long-term stewardship.
So the priority has to be stopping the bleeding first, preventing more loss.
Absolutely. Stop the losses from natural systems now.
Yes.
And then start that slow, deliberate restoration process. It's not either, but prevention is paramount.
And when we measure these changes, the sources are really insistent on needing deep samples and this equivalent soil mass method, ESM. Why isn't just checking the surface good enough?
Well, because management, like tilling, changes how dense the soil is. It compacts it or loosens it.
Right.
So if you just measure the concentration grams of carbon per kilo of soil near the surface, you might get misled if the density changed. ESM basically corrects for that. It makes sure you're comparing the actual amount of carbon in the same mass of soil before and after.
Got it. Comparing apples to apples, mass-wise.
Exactly. And you have to sample deep, at least 30 centimeters, ideally down to a meter, because the really stable carbon, the MAOC we'll talk about, changes slowly and often deeper down.
Okay, so let's get into those fractions. Beyond just total carbon, you mentioned POC and MAOC. These determine if carbon sticks around for decades or centuries.
Precisely. They behave very differently. First, you have particulate organic carbon, or POC.
POC, that's the fast one.
That's the fast one, the lay-by fraction. Think fresh plant bits, partly broken down stuff. It's the quick cycle, short-term storage. Globally, its average turnover time is maybe only 23 years. Microbes get at it easily.
Okay, 23 years, very transient. So what's the long-haul storage, the stable stuff?
That would be your MAOC, mineral-associated organic carbon. This is carbon that's been really processed, often by microbes, and then it gets stuck onto tiny soil particles, silt, and clay.
So it's physically protected?
Physically and chemically bound. This makes it much more persistent, its average turnover time, around 129 years. MAOC is really the goal for long-term climate benefits.
Right. Now, this is where it got really interesting for me in the sources. How do these two pools react when land is degraded, like with heavy farming?
Well, the POC, the label stuff, is super vulnerable. Makes sense, right? A degradation can wipe out up to maybe 74% of the POC. It goes quickly.
Okay, almost three-quarters gone. But the MAOC, the stable pool,
Even the MAOC takes a big hit. Losses there are around 45%.
hang on, 45% loss from the stable pool. That sounds contradictory. How can stable carbon disappear like that?
It seems like it, but it's mostly about physical disruption. Think about intense plowing. It just smashes apart the soil structure, the little clumps or aggregates that protect the MAOC.
So you break open the protective structure.
Exactly. You expose that previously safe carbon to microbes, and poof, it gets mineralized, lost as CO2. The protection is gone.
That makes sense. It's not inherently unstable, but its protection is fragile.
Yeah.
Okay, now flip it. We start restoring the soil. Regenerative ag, maybe. Which pool recovers first?
The POC usually bounces back quicker. You add cover crops, leave residues. That's fresh organic matter, so you might see POC levels jump 20–33% relatively fast.
Okay, quick gains in the short-term pool.
But MAOC recovery is much slower, and this is critical. It depends on the soil's capacity to bind more carbon. It's called the MAOC saturation deficit.
Saturation deficit, meaning the soil can only hold so much stable carbon.
Kind of. The mineral surfaces have a finite capacity to bind that processed carbon. If your soil's minerals are already full or saturated with MAOC, just adding more organic matter might only build up the vulnerable POC pool. You can't just force-feed MAOC indefinitely. There's a limit.
So building truly stable carbon depends on the soil's mineral capacity and the process that converts that temporary POC into the long-term MAOC, which brings us back to the biology.
Exactly. The microbes are running that conversion process. And this is where the bacteria to fungi ratio, the BF ratio, becomes so important. It tells you a lot about how efficiently carbon is being used and stored.
So a high BF ratio, lots of bacteria relative to fungi. What does that mean for carbon?
Generally, that's not great for long-term storage.
Hmm.
Think intensive agriculture, lots of tillage, maybe high nitrogen fertilizer. That tends to favor bacteria.
And bacteria are.
They're kind of the fast consumers. They break down simpler stuff quickly, leads to faster carbon turnover, more CO2 respired back into the atmosphere, and less complex microbial networks.
Okay, so high BF is fast turnover, more loss. The opposite then, low BF, more fungi. That's what we want.
That's what you typically find in stable natural systems like forests or maybe low-intensity pastures. Fungi tend to dominate there.
And fungi are the builders.
They're the slow, steady builders, yes. Fungal dominance is strongly linked to greater carbon stability, building up that persistent organic matter.
And the sources mentioned soil pH having a massive impact on this ratio.
It's incredible. Soil pH alone can swing the fungal versus bacterial growth ratio by something like 30-fold between acidic and alkaline soils. It's a huge controlling factor.
Wow. So changing the land use, the disturbance, the pH, it's literally changing the management team in the soil, favoring the quick spenders over the long-term savers.
That's a perfect analogy.
Yeah.
Which leads to the next logical question. Why? Why does having more fungi, a low BF ratio, lead to more stable carbon? There are basically three key reasons.
Okay, let's hear them. Mechanism one.
First is what's called necromass contribution. Fungal bodies, even after they die, are really good at resisting decomposition compared to bacterial bodies.
So dead fungi stick around longer.
Much longer. Their dead cells, their necromass, can actually make up a huge chunk, sometimes around half of the really durable, long-lasting soil carbon. So fungi contribute to stable carbon, both alive and dead.
Okay, necromass. What's the second reason?
Second, physical protection. Fungi grow as these long threads called hyphae. These threads physically weave soil particles together. They build the house, basically.
Creating those protective aggregates we talked about.
Exactly. They foster macro-aggregate formation.
Yeah.
These little soil clumps physically shield the easily decomposed POC and also the intermediate compounds that will eventually become MAOC from being rapidly eaten.
So they're like tiny engineers building safe spaces for carbon.
Precisely. And the third reason is efficiency. It's called microbial carbon use efficiency, or CUE.
Carbon use efficiency, meaning
How much of the carbon a microbe consumes actually goes into building its own body versus how much it just breathes out as CO2. Fungal-dominated systems generally have higher CUE.
so fungi waste less carbon. They incorporate more into themselves.
That's the idea. More carbon gets channeled into building stable fungal biomass and that persistent necromass, and less is immediately lost as gas. Higher efficiency, better storage.
This is fascinating. So the microbial community, specifically that fungal balance, is basically deciding if carbon hangs around for 20-odd years as POC, or if it gets processed and protected as MAOC for over a century.
That's the core linkage, yes.
Okay, so taking all this together, if we want real, long-lasting climate mitigation from soils, what are the actionable strategies? What should we actually do?
Well, the big picture goal, based on these mechanisms, is to try and mimic those stable natural systems. That means less disturbance, more diverse organic stuff going in, and actively encouraging that fungal community, aiming for a lower BF ratio.
So step one is obviously, don't make the problem worse.
Priority number one, always. Protect the carbon-rich ecosystems we still have. Avoid converting forests, grasslands, and especially peatlands.
Yes, peatlands are critical.
Absolutely. And re-wetting peatlands that have already been drained is a huge mitigation win. It stops massive ongoing CO2 emissions much faster than trying to build carbon back in mineral soils.
Okay, preservation first. Then, on land already being farmed, how do we nudge things towards the fungal side?
Practices that reduce disturbance are key. No-till or reduced tillage is a big one. It avoids physically destroying those fungal networks.
Right, let the hyphae do their work.
And increase the complexity of what you're adding. Agroforestry integrating trees and shrubs with crops is a great example. It provides diverse, woody inputs fungi-like, and studies show it can boost SOC by 20–26%.
What about actively adding microbes, like inoculants?
Yes, particularly in really degraded soils. Using things like AMF, arbuscular mycorrhizal fungi inoculants, can help kickstart those fungal communities and improve that crucial carbon use efficiency.
And we need to think about the fractions we're building, right? Not just total carbon.
Absolutely critical. Be fraction aware. We need practices that boost POC quickly, like cover crops or leaving crop residues. That's the initial gain.
But that's the vulnerable stuff.
Exactly. So those practices need to happen alongside conditions that help convert that POC into stable MAOC. That means managing soil pH correctly, promoting aggregation, ensuring the mineral binding sites are available and active. Just piling on POC without building MAOC is creating a carbon pool that's easily lost again.
So this whole deep dive really shows that managing soil carbon effectively isn't just about dumping organic matter in. It's much more subtle. It's about fostering the right microbial ecosystem.
It really is. It's ecological management at a microscopic scale. Understanding that interplay land use, the bacteria-fungi balance, how POC becomes MAOC, that's the foundation for truly climate-smart land stewardship.
We know how much we've lost, and now we're starting to understand the biological gears we need to engage to, well, slowly and carefully build it back in a stable form.
Exactly. Slowly, deliberately, and aiming for stability.
So here's something to think about. Consider the patch of soil nearest to you right now. If you actually knew its bacteria-to-fungi ratio, its MAOC saturation level, would that change how you or anyone manage that piece of land?
A powerful question.
The real challenge, it seems, is moving our monitoring and our management beyond just total carbon towards this more sophisticated fraction-aware approach. We need to make sure our efforts are actually building that long-term resilient MAOC, not just piling up vulnerable POC that could vanish with the next drought or the next pass of the plow.
That's the frontier, ensuring permanence.